So Markus, thank you very much for joining me here tonight, and I will talk a little bit about what is a circular economy. And maybe in my own simple terms is, at this point in time we seem to borrow from the earth in mining, we build big things and then in the end they end up somewhere in a waste. And in the circular economy we're starting to use more and more of what we use as waste and bring that back into the cycle of manufacturing and reuse. Can you maybe tell us a little bit about where we are in this space at this point in time?
But I tend to see it as a remembering what the earth does. It recycles itself daily. And we're just starting to remember that again. But unfortunately or fortunately, you need an economic incentive to make this happen. So we can speak about circular economy, but its true value is really only materialized if we can fund it, get the materials back from products, from the urban mine, from the complexity within that, and then circulate it back. But ultimately, money is required, economic incentive to make that work.
So when I think about, say, a mobile phone like this, it's a highly complex device, lots of elements in there. In the end, it has a very short lifetime, probably 2-3 years. Its technology is old, and I'll replace it, and this goes somewhere to a dump, most likely. How much is actually recyclable already in a device like this? Is there technology to bring it back to its original elements and reuse it?
Can I take that further to a simpler product?
Sure.
The most recycled metal is lead. And the reason for that is it's used mainly in car batteries.
Yep.
And it's collected from there, so the collection aspect of it is very high. Making it possible then to put it into a separate heap and actually recovering the lead. Now if you go to the products that you mentioned, which have got say 40, 50, 60 elements in them, becomes a fairly complex mineral. And depending on the one hand, if it's collected, and it comes from the urban mine into the material cycle, and it can be separated to an extent. If you've got the right technologies, the metals can be recovered. But the caveat is always thermodynamics. And as we are in an academic environment, it's even the second law of thermodynamics that is the most driving one, which is then directly related to economics, because we are diluting stuff. And that dilution affects how well we can recover it. And by the mere physics nature of the product, the elements and the compounds and the alloys have conflicting chemical properties. So you win some sometimes and you lose others. And there's no clear answer. But you can get a rough cut depending on the mix that's in the product. Getting back to the battery, it's mainly lead paste, and the recovery of that is very high. So in excess of 60%, depending on what measure you take. Okay. So it's a very highly recycled metal because of its sort of very limited type of application, relatively simple application. The battery producers will probably not like to hear that, but compared to a smartphone, they'll agree. So, and that's the limiting factors, is the complexity of the mixtures of materials, alloys, plastics. That's all part of a complex product that actually then makes the circular economy work or not.
So even at 60%, you actually surprised me a little that I would say so little can be recycled, and you say this is a really good achievement already and we're very high. So my question is then, in a way, can we do better from an engineering point of view? Could we design for recyclability rather than design for use?
Obviously, you'd firstly to design something that the consumer wants to buy it. If it's clunky and it's going to weigh a ton in your pocket and it's recyclable, who's going to buy it? So,
point taken.
So that's the beauty of products. You have to keep the freedom of the beauty in the product to have a market value and its functionality. going to functionality is ultimately, that is the limiting factor.
Mm-hmm.
If we go to a chair, we design that for recycling. It's got few materials. And you can just take it apart, even manually, and you can have different streams, and then the recycling rate becomes very high. If I say about lead, the battery part of that recycling is very high. I know we've designed the plants and we've built the smelters that do that, so if the lead comes there, the lead recovery is extremely high.
Mm-hmm.
But once again, it's a simple product. If you go to your smartphone again, how do you design for recycle a circuit board? You're the electrical engineer. It's got a functionality, so stuff is going to be connected.
Yeah.
So you can design certain stuff, sort of the more bulky material. But if you go to a LED lamp like we have above us here, in the LED bit, the light emitting diode, there are rare earths, and there's I think gallium and indium and that type of stuff, and it's very tightly connected.
Yeah.
And the properties are so different that if you want to recover it, you'll recover the indium and the gallium, but you lose the rare earths, or vice versa, depending on what you do. So yes, you can design to an extent, but then if you really want to get to the limits of it, then we truly need the engineering design approach, that you go right down to the thermodynamics of that mineral. Then you can at least understand what happens. And I'm saying that because at the moment we've just got a very nice LED recycling model where the recycling rate is fairly low because of this complexity.
Yeah.
People want to wish it up. They do very superficial eco-design. But if you really go down to the simulation, mathematical, thermodynamic level, you find the real recycling rate. And then you can innovate.
Mm-hmm.
And then you can start answering those questions better. But we are starting to do that. But there are conflicting worlds. The eco-design world and the engineering, process engineering world coming together, and that clashes still a bit. But we're getting there because it's ultimately based on good maths. We spoke about mathematics a moment ago.
Yeah.
And ultimately, if you get down to that level, you get unemotional, and then we get to good numbers.
So I accept that usability is a very important thing, and then engineers have to design for usability, and then recyclability will become a subservient, but an important aspect of it. So in some sense, you must also hate the fashion industry then, because they will design something for being thrown away very quickly. And in some sense, if you could design for longevity, that would also help the circular economy to some extent, because that way you have a more longer lifetime, and therefore the cost probably is amortized over a longer period of time.
Take the good clothing. We were speaking about clothing. Take a Chanel. It's still, after so many years, still classic.
Mm.
And the quality of the material is probably such that you can still wear stuff probably that is 20 years old, 30 years, and it'll still be fashionable. I think we live in a throwaway society where things are fickle.
Mm.
And we're not designing for quality, longevity, with good cotton, good material, that extends stuff for a longer time. And that's part of the circular economy as well.
Yep.
It's all about quality in the end.
Yes.
Recognizing, firstly, quality of nature, and bringing that quality into our lives. And that affects what we buy, what we use, what clothes we use. And perhaps you buy a little bit less stuff. And it's part of circular economy. But then, do we keep the economic wheel going if we don't buy? So that's the conflicting forces in this field.
So if we have a quick turnaround time, we want high recyclability, and if it's slower, we can have a bit less maybe. So given that there are all these constraints in its society, obviously, and economics as well, but also some real engineering aspects to it, how do you feel we should, as engineers, train the next generation of engineers? How should they start thinking about these aspects as part of the curriculum maybe, or should our students start thinking about this?
We started off with circular economy, is that connectivity is required. The feeling that we are using 1.5 Earths, and that we are on a limited capacity,
Footprint,
limited footprint. So, as I said earlier, engineering design is what engineers do well. And that is an absolute key to a circular economy, to understand the detail of the complex interactions of materials, flows, products, but all on an economic base. Otherwise, it's just nice words.
Yeah.
Engineers help with that. But what engineers also have to do is be very much aware of social aspect. Just part of the circular economy is collection.
Mm-hmm.
So if there are 100 mobile phones, but say 90 plus remain in the cupboard, because there's an emotional link to the telephone and it's not coming out of the cupboard or the woodwork, then it can't come into the cycle. So very much social aspect, social science in a way, but opening up the mind. So we call it, even in our own company, Outotec, de-siloing the thinking.
Mm-hmm.
We are still at universities living in our academic silos, and the circular economy demands to break those down. So engineers are a key, but economics is a key. But we have to speak together, and I believe the only language in the end is mathematics. It's ultimately the linking of flows of materials in rigorous simulation that you can link economics to, because you can make a study of the flow of money then in the depth that is required to understand what the value of waste is, because you can always count the gold in it, but the gold is not just a nugget, it's somewhere complexly linked, so to take it out also costs money. So you can't just count the gold, you have to count the context within in which it manifests itself. So opening up the silos and getting away from the classical demarcation of disciplines is is really required. Circular economy means, for me, that it's de-siloing. Nature is de-siloed.
Yeah.
Totally de-siloed. We are the silos. And look what the effect is on nature. But if we take the de-siloing into our life, recognizing that we have the tools to actually do something as engineers, that's a unique skill as design. Engineers do that. That we've got a very important role. But then we shouldn't be electrical engineers or civil or mechanical, chemical engineers. We are engineers that design.
Yep.
And we speak to each other, and we've got an integral part in that role. And we have to also be eloquent in that.
Yeah, because we have to convince others.
We have to convince,
about it,
yes. But then we've got a great role to play.
Yeah. It's actually, you make the Melbourne model sound fantastic, because that's exactly what we try to do with our engineers, to bring these things together. So maybe a question about optimism or pessimism, because you keep on referring back to 1.5 Earths that we are using right now, and I think the World Wildlife Fund makes these type of statements quite often, and so I accept it's 1.5 times Earth that we are using right now. The population is even growing even further. If we keep on doing like what we are doing now, we're just going to use more resources, even more Earths than what we have available. So are you an optimist or a pessimist? Can we do this? Can engineers actually design to such an extent that we can double the population maybe, and yet still live within the capacity of a single Earth? Or do you think we have to go and mine the planets?
I think I'm an optimist, because we are part of this Earth. I lectured yesterday, I come here, I lectured, and the young people, we as the older generation, are the gatekeepers, or the guys that are taking the people from here to this very daunting and interesting environment where we have 1.5 Earths, and this is a daunting problem to solve. So if we are not optimistic, and we don't light up that fire in your young people and give them the right tools, not the fluff tools, not the hand waving, real tools, which we do give, you give them hope. So if we don't have any hope anymore, that won't be a good situation. So what we should be doing is, and that's what I try to do, is actually to guide. And even drop these messages, please. If you drink a beer, just recognize that there's many liters of water that you are consuming together with that beer. Be aware. And by that, really trying to change the way we think, how we consume, because we are becoming more people. That is a constraint. So we have to change our behavior. But we can't just say, well, we now here, let's just drop everything and just be pessimistic. Otherwise we wouldn't be sitting here and trying to change the world. And I always say to students, come on guys, change the world. This is your opportunity.
You mentioned the league table of companies. You're the third most sustainable company on earth, Outotec you work for. Who are the number 1 and 2, and how do you get on the league table? So how would a university like us come on the league table of most sustainable companies or corporations?
It's your footprint of what you do as a company. And it's interesting to note that a metals company is so high up.
That's right, yeah.
And that's interesting that the mindset is changing. It's not just about just one-way extraction. Is obviously you need to extract metals because there's a growing population. There's losses, there are inefficiencies in the system, but we are more and more recycling back, which is part of the circular economy. So you're trying to use less. So it's that playing field where these companies are operating in. So they're trying to change things. And we need young, innovative young graduates to come into these companies that are trying to play in this field. And it's tough, because you're going into uncharted territory partially. But we're doing it, and we're trying to do it.
But that's the innovation, that's the future basically, so that's the excitement.
Yeah, that's what you should do.